Yeah, the recording has started. Uh so we answered the first part, so there is no contention there. So now we now go to the second part for the maximum possible work. The so so the part that we calculated last week, we are calculating the part where we are looking at the actual amount of what the amount the actual amount of work that has been done, and then we're also comparing it with the possible maximum amount that can be produced. So now you know that for any equation, when you get the actual and what you expect, then you can actually have an equation of what? An equation of efficiency. So what efficiency basically does is you are simply asking yourself to say, really, from what we were expecting, how much have we gotten? Right? Let's say someone studied for many hours and then they don't do well on a test. Then you can rate their efficiency to say, but this person put in so much effort. Why is it that they didn't really do well? So that gives you an idea of that person's what efficiency. Okay, so we already calculated the actual work that was produced, and I explained how to do it. You can check the previous video. Then for the maximum work possible, so here the only thing that was the number of moles are the same, the Faraday's constant is the same, but the only difference that for the maximum possible work, it's anyway, let's do the calculation. So it's going to be maximum work, so it's going to be the maximum work, which is W max is equal to negative number of what's that? Number of electrons transferred, Faraday's constant, and the E value. Not necessarily the standard E value though, I would say. Yeah, but anyway, So then, having done that, then you now just have to start plugging in the particular values. Okay, so you have to start plugging in the values. So you know that the work you can also relate it to that minus Q E, where we discussed last week that Q is basically the number of moles times what? Times Faraday's constant. Okay, so we did that. So now let's now answer this question. So the number of moles, like we said last week, the number of moles which were actually acting in this reaction were what? Were 1.33. Okay, so that negative there. Okay, 1.33 moles of electrons times Faraday's constant. Huh? So Faraday's constant. So for how we derived these equations, you can look up the previous video. Okay, so there times what's the E. So the E value is 250 J C. Okay, so that's joule per column. So pay that's over and that's on top, so they can cancel. That's on top and that's over, so they can cancel. So you see that we're only remaining with what? Something in terms of joules. So meaning the maximum work. So that's about it. So now, yesterday or rather last week, we calculated the actual amount of work that was done, and then now we've calculated the maximum amount of work that can be done. Of course, you can see between the two equations, the only difference is what is in the voltage, isn't it? The voltage, the actual voltage was 2.10, then the maximum, the possible one was 2.50. So that's where the difference was coming. So then to find the efficiency you are going to say, for me to find efficiency is, so efficiency is going to be the actual work over the maximum possible expected, right? So that's so the actual work done over the maximum possible work that can be done times 100%. Okay, so times 100%. So once you've done that, then you want now to just plug in the values. So the one for the actual work done, yeah, last week we calculated, and now we've calculated this. Then, oh, times 100%. Okay, so then what we are then going to have is 83.8%. So you see that actually the the efficiency of this whatever cell we are looking at is not really bad. I think it's fair. It's fair. So now we can now proceed then to look at something. So now we now want to be able to relate the potential of a galvanic cell to a concept that you call free energy. So free energy, though, we'll talk about it more when we start looking at thermochemistry. But free energy, you're just basically trying to look at how the reactants and the products, the energy difference really between the what between the reactants and the what and the products. That's basically, but not actually. So, but we'll dive into that. So then, we'll dive into that when we do thermochemistry. So then how do we derive the equation relating the galvanic cell to free energy? So how we do this is, let me wrap this so we can start a clean chapter. So how do we do this? So how we do this is we've already understood that the maximum work done is equals to what? To the change in free energy. So then, what do we know about the maximum work? The maximum work, we know that work is what? Work is negative Q and then the cell potential max. Then we know that Q is number of moles times Faraday's constant. So substituting the Q there means that we have negative number of moles, Faraday's constant, and the Emax. That makes sense, right? So then what? So now substituting this into the first equation that we started with, we then have mm, free energy is equal to minus number of moles times Faraday constant and Emax. So now under standard conditions, so standard conditions is where you just put those to my tiny zeros, to my superscripts. So for standard conditions, so for standard conditions, so this is what you use. So you see the difference is just those superscripts that we've put there, those that look like my zeros on top. So for standard conditions, so then why is this important is that because this actually tells us that we can actually be able to calculate and determine whether a reaction is spontaneous. Because what is the principle for a reaction to be spontaneous? It has to have a what? A free energy change of what? Of negative. And we know that for a cell to progress, this value of E is positive, isn't it? So if this value is positive, and then you've got a negative in front, meaning for a cell, for a galvanic cell, since it's got it to for a cell, it will run in the direction that gives a positive E value. And positive E value and the Faraday's constant is positive, the number of moles is positive, but there's a negative in front, right? So meaning that when the cell goes in that direction, your change in free energy is going to be negative, and that is a condition for spontaneity. So it means that this cell can be able to progress and is what is spontaneous. Okay, so now let's look at an example. So then, mm, so that's how the probably your tutorial sheets are with questions like this. So calculating, so using the data in table 18.1. So the data in 18.1 is just where you are looking at the reduction half reactions. So it's where you are looking at the reduction half reactions, and then so that's the table 18.1. So now using that data, calculate the what? Calculate the change in free energy under standard conditions, because those values in the table are under standard conditions. Then now tell us, is the reaction spontaneous? So what they basically want you to find is that is your value for the change in free energy, is it negative? If it's negative, it means that this reaction is what is spontaneous. That makes sense, right? So then let's proceed. So, what reaction? So that's done. Then that. Okay, yeah. So that's about it, right? So now you have to find from that table 18.1, you have then to write the what? The reduction half reactions. Okay, so we go to that lovely table there, and we are going to find that copper. Then this is going to be then for this. So that's ion 2. So for that ion 2, what we are going to have is um, trying to look at the actual table so that we don't make any mistakes. Okay, I don't know. Anyway, yeah. So then what we are going to have there is ion. Anyway, I don't know why, but I can't really. Anyway, yeah. So when you okay, I found it. So it's negative 0.44 volts. So now remember what we said. Which one would be the cathode? The cathode is the one that has got what? That has got the higher E value, and we see clearly that it's this one. So meaning this ion has to be moved where this equation has to be reversed. Okay, so reversing it is going to become, so we are going to have that, and that. So the value of E is going to change, right? It's now negative E, For this one, it's now going to be positive that and that. So now, like we said that time, so this is our cathode and this is our anode. So then, what then is important then to do is then to say how many electrons were transferred in this reaction. So then what you do is you want to make a single equation from here and say you are adding these equations. Huh? So then you are saying you cancel the electrons, you cancel the electrons, then you are going to have that. So going to have that. Of course, put state symbols, then you're going to have then you're going to have the copper there, right? Okay, so you see that how many electrons were there from the balanced equations? There were two electrons, right? From the equations that we had. And since both electrons were two, so we didn't have to multiply any reaction to balance the electrons. They were already balanced. So then you now bring up the equation for this. Okay, so what's going to be what's your number of oh, we haven't calculated the E cell. So the E cell is going to be what? The E cell is going to be um what we do is we say so the cathode, and we've gone around this. So the cathode and then the anode. So you can do the adding. Anyway, we discussed this in the previous videos. So let's just write the values. In case you're not clear about this, you can check the like just on how to find the E cell. You can check the previous videos. But on what we are focusing on, in case you're not sure, you can ask. So then you see now there we've got that. So for us to find this, we're going to say negative. How many electrons were transferred? You've got two electrons here. So meaning your N is 2. Faraday's constant, that's a constant. It's always the same. And we've calculated our E cell. So meaning we can say negative the number of electrons there too. What's Faraday's constant? Oh my goodness, something has entered my eye. Okay, so 2 ish. Sorry, something has just entered my eye. Okay, so that's ish. What's this? Okay, so that's 2 moles electrons. So that's 2 moles of electrons. Then Faraday's constant, which is going to be okay. And let me just cancel something that has come up on the laptop. Just cancel it. Okay. Yeah. So Faraday's constant is going to be negative. No, sorry, 96,485, which is going to be Coulomb per mole of electron, and then so per mole of electron, then the E cell. So let me just write the N somewhere there. So the N is 2 there. Then the E cell is what? That's positive 0.78. Now for this one, we prefer to write joules over coulomb. But since joules over coulomb is the same as volts, but we love using this because there we can see the cancellation. So it makes the work clear. Okay, so once you do this, you then get your value of 1.5 times 10 to the power 5 joules. So that's the negative G. So then how then do you explain that this reaction is spontaneous? So you explain and say uh, the process is spontaneous and it's been indicated by both a negative sign of a negative sign of free energy and a positive sign of what? A sign of E cell. Since these are the what? These are the conditions for spontaneity. So both the negative sign for free energy and the positive sign of E cell. So that's how you go about answering these questions. So should we do a second equation? Should we look at a second example? People, can we look at a second example? Okay, when the E value is negative. So it's not really about in what condition is negative. It's just that's why certain reactions cannot take place. Remember, that's why we are saying this one where the E cell is positive, right? The reaction will occur spontaneously. So there are certain equations where they can't occur on their own. They will need a push. They will need some energy. So those are reactions where the E cell is negative. So they don't have the spontaneity. Okay, so they are not spontaneous. That's to say, right? So there are many reactions, of course, yeah, that would require a push for them to occur. And this is the next example that we'll look at, which just focuses on exactly that. So the second example is going to be, uh, let's look at here, there. So using the data from table 18.1, predict whether one molarity of nitric acid will dissolve gold metal to form 1 mole of gold ion. Okay, so that's the gold ion. So here then you have to write the equation of how this is going to occur. Alright? Okay, great. So then what you do for this one is, so that's where you have to be able to write equations really well and all those things. So what you then do is, since we've already done how to do equations during stoichiometry, so I'll just write them. Always remember to write to include state symbol. Oh, but for this one, since it's just number 10, it's good to make it a habit. So we have that. So this is what the table shows for nitric acid. So it would be good to look at the table, familiarize yourself with how to find these things on the table. So that's about it. So if you want to locate it on the table, mm, start looking for nitric acid, and there you'll have it. So maybe for the sake, it's always good not to take things for granted. So let me not take things for granted. Let's just ensure that everyone can find it. So you've seen it here, right? Where I'll put a tick. So where I'll draw a line. Do I enter drawing line? So you see it, right? Yeah, so that's the one, you've seen? So that's the one that we are making reference to. So you can see that it's a positive there. It's positive, okay? I know it's good never to take things for granted. Okay, so we know that that one is the E value is what? 0.96 volts. 0.96 volts. Then for the gold, remember everything is written from the perspective of reduction. So it's good when you start like that, because then you will then determine from here which one will be the cathode and the anode. Then you can write your full equation. So this will be gold like that. Then your E is going to be again the same way we went on this on that table. You can go on that table and say gold, 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 gold. Gold, you see that it's positive 1.5, positive 1.5. So you see that's positive 1.5 volts. So now, when you look at this interesting thing, um, okay, let's just confirm. Okay, yeah. So now, when you look at this particular reaction, under normal circumstances, uh, the gold would be the what? The gold should be the cathode, isn't it? Since the gold is the one that's having a higher, what's this? Reduction potential, right? But what the question is actually asking us is the other way around, because they're asking us to predict whether one molarity of nitric acid would dissolve metal to form uh, ions. So what they're basically telling us is we are moving from this to this. I hope everyone has understood the question. So we are dissolving the gold into this nitric acid to form ions from the what? Ions from the metal solid. So if we are forming ions from the metal solid, it means that it's this reaction that has to be reversed. I hope that that point has been taken as to why, even though this one is more positive in terms of reduction potential, but what the question is asking us entails that it's this same one which has got a higher one, which has to be what? Which has to be reversed. Because it's this solid which is dissolving into, we are trying to find out whether it's able to dissolve. So that's that. So the E has changed to negative 1.5, to negative 1.5. So when you look at that, what then do you do? You now combine the two equations, of course, being this one and this one. This one will be the cathode, and this one will be the anode. So, of course, electrons cancel. Then you can write your things. Okay, so let's write that. So gold solid, then that aqueous. And so you've seen that I'm writing state symbols. People lose marks over these things. So okay, great. Hello? Okay, okay, sure. Yeah, no, I'm there. Just that I was just trying to finish the writing. Okay, great. I know, but it's good to ask, because if you can find that I've been disconnected, yeah, that it's good to ask. It's good to ask. Okay, yeah. So now, how do we find the E cell? So to find the E cell, we are going to say that is going to be the cathode. Okay, so the cathode, if you want, plus anode. So what then you're going to get is you're going to get the cathode. Remember, it's the one 0 point, it's the one that's being reduced. Yes. Then the anode, it's a plus, but of course mm, because of the negative there, so it becomes that, right? Yeah. So then you're going to have what? You are going to have a value of negative 0.5454. Again, your Zumda gives this in a okay. So your Zumda gives this in a different manner, and I always want to clear this because many people are think maybe either one has made a mistake or something. So your Zumda gives it like this, which simply says which simply means you just get the potential for the cathode, and the conversion has already been done. So you just put in the original E value. So for this one, you put in the one before the conversion has happened. But for this one, it's easy to make mistakes. That's why I prefer the one that I did at first. Okay, but I just thought I should bring that point out. So here we know that our E value is negative. So we know that okay, that's a good sign. Anyway, but a bad sign for the reaction. So from there, we now look at our N. How many electrons were transferred? We see that electrons there were three, huh? Three electrons. So meaning our N is what? Our N is going to be 3. So if our N is 3, then we are going to say, uh, so we are going to say change in free energy is going to be N, that's number of moles, then Faraday's constant, then this E cell. So number of electrons, 3 moles of electrons. So 3 moles of electrons, and then what's Faraday's constant? So Faraday's constant is 96,485. So 485, and that's going to be Coulomb per mole of electron. So per mole of electron. Then what is the E cell? So the E cell is negative 0.54 volts. So then here we are going to get a what? We are going to get a positive value. So let me do the calculation. 96485 times 3 times 0.5.0976. Okay, then we are going to have that. So we get positive 1.56. Let me just look at the zeros there that we have. Mm, Look at the zeros that we have. So that's what? That's 1, 2, 3, 4, 5. Okay. So 5, yeah. So that cancels that. What else? So again, preferably here, we want to use these signs which are going to be easy to cancel, right? So you cancel the C remain with the J. So we see that our free energy is what? Is positive, and our E cell is negative. So what this means, so how you write this is, since the E value, so since E cell value is negative and the change in free energy is positive, therefore, and you have to write this because these are marks. Therefore, the process will not occur. Will Anyway, the process is not spontaneous. Now let's just make it simple. It's not spontaneous. So yeah, so that's basically how you deal with it. So The key thing is just the concepts. Once the concepts are understood, everything just becomes what? Everything becomes a build up. So then, having talked about that, we can now talk about the concentration cells. So then, what is a concentration cell? So you may have noticed that all the cells that we've been talking about, we've been having different things at the anode and different things at the cathode. By different things, I mean different species and different everything. But then there are going to be particular cells where uh, everything that's in them, or rather both the anode and the cathode, they've got you could say the same amount. Okay, so but before we can dive into that and talk about the concentration cells, let's talk about how we can predict uh, changes in the E cell value. And how we do this is you've already done equilibrium. So you looked at Le Chatel's principle, which basically says that if you've got so much of a reactant, uh, then the uh, then the reaction want to go forwards so that uh, so that more of the product can be formed and then the reactants can be used up. In one way or the other, you are balancing the two sides, right? So that's what Le Chatelier's principle basically states. And conversely, if you've got more of the product, then the reaction is going to go backwards to try to reduce the concentration of the product and increase the concentration of the reactants. So using that understanding, we can, because we know that for all the standard for all the standard cells that we've talked about, all the concentrations that we are dealing with are what? They are one molarity. Okay, so it then means that if we either increase or decrease the concentration of either the product of the reactants, we can be able to predict whether the E cell is going to be large or small without even using the next equation. The next equation comes in when we want to find the actual E cell value. But understanding the Le Chatelier's principle will be very helpful. So let's now look at this particular reaction there. So you've seen there the one that not okay. Okay, let's do this. Let's zoom it so that we only have one equation showing. So when you look at that particular reaction, right, it's got a cell potential of 1.36, right? Yeah. Now, if we then increase the concentration of Kesha, I think that no, I think okay. Anyway, if we increase the concentration of that reactant, so you've seen those curly brackets signify concentration. I'm sure you've done equilibrium, so yeah. So those curly brackets there, they mean what? They mean the concentration. So what will happen if the concentration of that reactant there, which is Ce 4 plus, huh? What would be the cell? What will happen to the cell potential if we raise its concentration to greater than 1 molarity? Remember, all the things in solutions under standard conditions, all the concentrations are 1 molarity. So now we are increasing the concentration of a particular reactant. So what will happen on the E cell? The E cell is going to what? To increase. Okay, the cell potential is going to increase because according to Le Chatelier's principle is that the increase in the reactant concentration is going to favor the forward reaction so that the reactant gets used up and then they stabilize the concentrations with the what? With the products. That makes sense, right? Then, on the other hand, if we increase the concentration of the products, such as the copper 2 ion or the Ce plus 3, if we increase the concentration of either of the products, what's going to happen is that the reaction will then want to go backwards, to try to produce some of the what? To reproduce some of the reactants so as to try to balance out the what? To try to balance out the concentrations. And what will happen in that case? The cell potential is going to decrease. That makes sense, huh? So let's now look at these examples. Okay, great. Let's just digest these wonderful examples together. So, okay, can someone tell me what will happen in the first case? Where, so remember, for standard cells, all the concentrations are 1. So you get anything above 1, then they've increased it. Anything that is 1, then they've not changed it. Anything below 1 molarity, then they've decreased it. Huh? Okay, great. So now, can someone tell me what would be happening to the E cell value in part A, where we've got the aluminium ion, which has been raised to a molarity of 2, and and that Mn2 plus has remained the same. What will happen to the cell potential? Can someone tell us and explain why? Please, let's respond. Okay. Yes. Yeah, that's very, very good. Thank you so much. So we are increasing. So you always have to check, is what has been increased. Is it a product? Is it a what? Or is it a reactant? And we could see there clearly that it's actually the what's this? It's actually the product, right? So according to Le Chatellier's principle, so the reaction has to go towards the left to try to ensure that it makes more of the reactants. Okay, so that's something that's important to take note of. Then what other thing can we talk about? Now B, can someone help us with B? Okay, so you're saying that the cell potential will increase, right? Yeah, exactly. Thank you so much. Yeah, so you see, I mean, yeah, so these are some questions that they like in your. I think they should be one in your tutorial. That's if my memory serves me right. But yeah, so that's how you understand these questions. Then we now go to the concentration cells. So what are concentration cells? This was something that I was about to talk about in a short while, or rather earlier on. So, with the concentration cells, I'm sure you may be aware that all the cells that we've been talking about so far, they've been having different components on the aspect of on the uh, on the cathode and on the anode. But then there are certain times where you can actually have electrons, okay, where you can have particular electrons where where you can have certain cells where on both sides, on both the anode and the cathode, you're actually having the same components, but they are just at what? But they are just at different uh, concentrations. Now, what happens with this is that you have then to be able to explain and understand where will the electrons be going to. Okay, so you've got the a cell where the things which are on the cathode and the things which are on the anode, they are the same components. Like for this example we are looking at, on your far left, the one on top, you see that on the right you've got copper with molarity of 1. Then on the left, you've got copper 2, the same copper 2 with a molarity of 0.0 0.01 molarity. So now the question is, where will the electrons be going to? Okay, in which direction will the electrons be going to? So again, the concept here is the same with the almost like the Lecheterians, right? So look at what's happening. The right has got a lot of copper 2 ions. The left has got fewer copper 2 ions. So in which direction should the electrons be flowing to ensure that they try to equalize the the copper 2 ions on both sides? So the electrons have to be flowing from the left where there is few ions, because when the copper that is on the left, the more it's losing electrons, it means that the copper 2 concentration on the left is increasing, and then those electrons are going on the right where there is the copper 2 ions in a higher concentration. But as those electrons will be going on the right, they will be they'll be reducing those copper 2 ions to become copper solid, right? And what's going to happen is that, so you see that the copper 2 ions on the left will be increasing, and then the copper 2 ions on the right, where they were a lot, they'll be decreasing until they reach at a point where we could call some sort of equilibrium. Does that make sense? So what happens is that the electrons are going to flow from where there are few ions. Okay, so you see here the electrons are moving from where there are few ions, so that as the electron as those as that copper on the left with a small concentration, as they are losing electrons, the copper 2 ions amounts are what? Are increasing. And as they are increasing, they are going to the right to reduce the copper 2 ions, and then so on the right they are decreasing and on the left they are increasing. In that way, their aim, remember their aim is to what? Is to stabilize the concentrations there. Okay, so that's something that's very, very important. So to stabilize this particular cell, to this galvanic cell, the electrons will move from the left to go to the right. And another example that we can use just to highlight this is, let's look at figure. Where is figure 8 point? Let's consider which where is figure 8.9? Okay, anyway, since there is nothing else, let's just use. Okay, so a cell in which both compartments have the same components but at different concentrations is called a concentration cell. Huh? Yeah, so that's that. Huh? So the difference in concentration is the only factor that produces a cell potential in this case. So remember, if these two, the anode and the cathode in a concentration cell, if they've got the same concentrations, the anode and the cathode, they won't be any there won't be any changes, or rather there won't be any what can I say? There won't be a voltage, okay, if the concentrations are the same. So now figure 18.9 we see here on the left, you've got something, you've got zero point 0.1 silver ion. On the right, you've got 1 molarity. So where will the electrons go? Electrons will be moving from the left, okay, going to the right. So now, can someone now answer this question? Let me hide the answers. So look at this picture, and can someone tell us where the electrons will be going to? From where to where? Okay, but there's okay, yeah, let's hide it like that. So, where will the electrons be going to? Just say left or right or vice versa. So, where will the electrons be going to? Okay, so why would they be moving from left to right? Okay. What? Can you repeat that? Okay, so then why should the electrons move if they are few? No. Yes. Okay, okay. Thank you so much. That's very great. Though not to stabilize, but to equalize. Huh? Yeah, so to attempt to equalize, but that's very correct. So you see, so you see, you don't really have to memorize, right? It's just when once you understand, someone can wake you up and say, look at this galvanic cell. Where would they? How would the electrons be moving? And you can give an answer. But if you memorize it, you have to first, scratch your brain. So otherwise, thank you so much for that wonderful answer. So electrons will flow from the left to the right. Okay. That's great. So now let's now talk about the next equation. So what's the next equation? So we've basically been looking about, we've actually been actually predicting what answers we are going to get from the next equation by saying no, the E cell is going to be smaller, it's going to be larger, it's going to be. But now someone thought and said, okay, yes, we can predict that it's going to be larger or it's going to be smaller, but by what margin? Is it going to be smaller? You get my point, right? By what margin is it going, or by what margin is it going to be large? So that's where the next equation comes in. Because from here you can be able to figure out what the E cell is going to be under non-standard conditions. Non-standard conditions. Okay? So we are going to derive it together. So how do we derive it? Here we're just going to use the same since it's not pretty much complex. So that the first equation on top, I'm sure you've seen that in thermochemistry. So now what we can do with this particular equation is, since we now know that the change in free energy is the same. Anyway, I think let's just write this. I think writing it will be easier for us to grasp it. So uh okay, so there you have it. So that's the equation. Now we've already realized from what we are doing that actually the change in free energy is equal to number of electrons, the Faraday constant, and the what, and the E cell. And we're using that as zero when we're looking for the standard. Then if it's not standard, we also do it like what? You do it like that. So you see that this one goes there and this one goes there. So tomorrow we'll basically be looking at the next equation, do some questions, and look at how corrosion occurs, look at electroplating. Then that should pretty much finish the what's this topic, and we can go to thermochemistry. So when we continue tomorrow, we'll be looking at the next equation. So are there any are there any questions? Are there any equations? So tomorrow we'll look at the next equation. Yeah, but are there any questions with regards to what we've done?